The James Webb Space Telescope has been researching the slightest items for replies about the universe. This NASA's new eye above has been capturing amazing pictures of stars, huge planets, and galaxies. Regardless, at last, something surprising has been found, something so gigantic that it could shake the very foundations of everything we understand. It has researchers scratching their heads, questioning whether it could redefine our understanding of the universe. Join us as we explore how the latest discoveries of the James Webb Space Telescope could change our comprehension of the cosmos. When we investigate the edge of the universe, we are discussing the observable universe. The observable universe appears to be a window through which we can glimpse the vastness beyond. It includes everything we can currently see, measure, and research using our telescopes and space probes. It is a collection of star systems and celestial bodies within our grasp to comprehend. However, the observable universe is just a small part of the entire universe. Imagine it as a slice of a gigantic cosmic pie that we are able to study and understand, while the total size and shape of the universe at large remain a mystery. Researchers estimate the width of our detectable bubble to be around 93 billion light-years. A light-year measures the distance that light, the fastest thing in the universe, travels in 1 year, around 5.88 trillion miles or 9.46 trillion kilometers. So, when we talk about the breadth of the observable universe being 93 billion light-years, we are referring to an enormous stretch. Around 13.8 billion years ago, the universe burst into existence in an incredibly powerful event known as the Big Bang. Since that immense explosion, the universe has not only been expanding, but also evolving. Mysterious forces like dark energy seem to be accelerating this expansion, pushing the boundaries of the universe even further apart. As the universe expanded, matter began to cluster together under the influence of gravity. This gravitational force brought particles together, giving birth to magnificent structures, stars, massive galaxies, and eventually planets like our own Earth. Imagine the universe evolving over time as these giant structures formed, shaping the extraordinary, yet ever-changing phenomena we see across the cosmos today. Despite its vast size, the universe is incredibly empty. If we were to shrink our entire solar system to the size of a quarter, the nearest star would still be about the length of 2 soccer fields away. This immense scale extends within our own Milky Way galaxy, which is just one among billions in the observable universe, giving us a sense of the boundless expanse of space. Now, you might ask, why can't we see everything that exists in the universe? There are several reasons for this limitation, the most fundamental being light. Although it is the fastest thing known, light takes time to travel through space. This means that when we observe distant objects, we are essentially looking into the past. The farther an object is, the longer its light has taken to reach us. It is like peering through a vast time machine, unraveling the history of our universe as we observe galaxies millions or even billions of light years away. The expansion of the universe also plays a role in this limitation. Imagine dots on the surface of an expanding balloon. As the balloon inflates, the dots move farther apart. This same principle applies to the universe. Galaxies are drifting away from each other as space itself expands. This expansion causes light from distant objects to undergo a phenomenon called redshift. Essentially, the wavelengths of light stretch as objects move away, shifting toward longer wavelengths and often appearing reddish in color. Given these factors, light's travel time, the expansion of space, and the universe's constant motion, it is no surprise that we have yet to see everything the universe has to offer. Even with our most advanced telescopes and technology, our view remains limited by these fundamental cosmic properties. The quest to understand the possible edge or limits of the universe has fascinated countless minds across various disciplines. While definitive answers remain elusive, 3 prominent theories have emerged, each offering intriguing perspectives on the nature of space. 1. The infinite universe theory. This theory suggests that the universe expands endlessly, without a discernible edge. It aligns with the cosmological principle, which states that the universe looks the same from any vantage point. If this principle holds, it implies that the universe has no boundary and stretches infinitely in all directions. 2. The finite but unbounded universe theory. This view proposes that while the universe may indeed be finite, it lacks a clear edge. Instead, it might resemble a vast, curved space, similar to Earth. If one were to travel in a straight line forever, they would eventually return to their starting point, much like circumnavigating the globe. 3. The multiverse hypothesis. This fascinating theory suggests that our universe is just one among countless others. Imagine an infinite number of parallel universes, each with its own physical laws, constants, and properties. These universes may be completely separate or interconnected in complex ways, forming a vast and intricate multiverse. The James Webb Space Telescope, unraveling cosmic mysteries. The James Webb Space Telescope, JWST, stands as a symbol of scientific potential, illuminating the mysteries of the universe's origins. This groundbreaking instrument has unparalleled capability in exploring the ancient past of the cosmos, allowing us to look further than ever before. The JWST is a technological marvel, specifically designed to observe the universe with remarkable precision. Its infrared capabilities enable it to detect faint emissions from ancient stars and galaxies, unveiling cosmic remnants that have endured for billions of years. A groundbreaking study published in the prestigious journal Nature revealed the JWST's discovery of 6 massive galaxies, dating back between 500 million and 700 million years after the Big Bang. Astonishingly, these ancient galaxies are far larger than expected, challenging the prevailing theories of galaxy formation. Their rapid development in the early universe is truly mind-blowing. What is remarkable about these discoveries is the complexity of these early galaxies. Contrary to previous assumptions that galaxies form gradually over time, these colossal structures exhibit a level of sophistication comparable to our 13-billion-year-old Milky Way galaxy. The sheer number of stars within these massive galaxies exceeds expectations. Some boast a total mass several times greater than our Sun, with one galaxy potentially having a mass up to 100 times that of our Sun, surpassing even the size of our Milky Way. The JWST's unmatched ability to explore the hidden depths of the universe is due to its use of infrared light, which falls outside the visible spectrum of the human eye. This remarkable feature allows the telescope to capture the faintest signals from the ancient cosmos, essentially acting as a time machine, transporting our vision back 13.5 billion years. A revolutionary discovery. The continued discovery of these massive galaxies, nicknamed universe breakers, has redefined our understanding of cosmic evolution. It is like rewriting the history of the universe, a stunning revelation that challenges many of the models we had established for early galaxies. The James Webb Space Telescope, JWST, is not only reshaping our understanding of galaxy formation, but also challenging long-standing theories about the early universe. The sheer size and complexity of these ancient galaxies force scientists to reconsider their models of cosmic evolution. Previously, astronomers believed that galaxies slowly accumulated stars and mass over billions of years. However, the JWST's data suggests that some galaxies formed rapidly, reaching enormous sizes in a relatively short period after the Big Bang. This discovery raises fundamental questions. How did these galaxies grow so quickly? Did star formation occur at a much faster rate than expected? Are we missing a key element in our understanding of the early universe? One possibility is that our current models of dark matter and gravity may need revision. Some researchers speculate that dark matter, the invisible substance thought to make up most of the universe's mass, may have played a bigger role in accelerating galaxy formation than previously believed. Others suggest that primordial black holes, formed in the earliest moments after the Big Bang, could have influenced early galactic structures, acting as gravitational anchors that sped up star formation. The mystery of dark matter and dark energy. As we peer deeper into the universe, we also confront one of the greatest mysteries of modern physics: dark matter, an invisible substance that holds galaxies together through gravity. Dark energy, a mysterious force driving the accelerated expansion of the universe. Together, dark matter and dark energy make up about 95% of the universe, yet scientists cannot directly observe them. Their existence is inferred from their gravitational effects on galaxies and cosmic expansion. The JWST's observations may provide new clues about how dark matter shaped early galaxies and whether dark energy has been affecting the universe's growth differently than we assumed. Could JWST detect alien life? While the JWST is primarily focused on observing distant galaxies, it is also a powerful tool in the search for extraterrestrial life. By analyzing the atmospheres of exoplanets, JWST can detect chemical signatures that may indicate habitability or even life itself. Some key targets for the telescope include TRAPPIST-1 system, a group of 7 Earth-sized exoplanets, some of which lie in the habitable zone of their star. Proxima Centauri b, a rocky exoplanet orbiting the closest star to our solar system, with potential for liquid water. Hycean worlds, a new class of planets with vast oceanic surfaces and thick hydrogen-rich atmospheres, which may support microbial life. The JWST's infrared capabilities allow it to analyze chemical compositions in planetary atmospheres, searching for signs of water vapor, methane, carbon dioxide, and even oxygen, all potential indicators of life. If the JWST detects a planet with an atmosphere similar to Earth's, it could be one of the greatest discoveries in human history, evidence that we are not alone in the universe. What's next for the James Webb Space Telescope? The JWST is still in its early years of operation, but its discoveries have already begun rewriting the history of the universe. Scientists now face a thrilling challenge: revising models of early galaxy formation, understanding dark matter and dark energy on a deeper level, searching for potentially habitable exoplanets. Upcoming JWST missions will focus on exploring the atmospheres of exoplanets in greater detail, studying black holes in the early universe, investigating how the first stars and galaxies were formed. As the JWST continues its mission, it will push the boundaries of what we know about space, time, and the origins of everything. Each new discovery brings more questions, but also more wonder, proving that the cosmos is far more mysterious and beautiful than we ever imagined. The future of space exploration. The JWST is just the beginning. Future missions like the Nancy Grace Roman Space Telescope and LUVOIR, Large Ultraviolet Optical Infrared Surveyor, will expand upon JWST's discoveries, offering even more precise observations of the cosmos. With each new telescope, we move closer to answering some of humanity's greatest questions. How did the universe begin? What is the nature of dark matter and dark energy? Is life elsewhere in the cosmos? The universe is vast and mysterious, and as the JWST continues to uncover its secrets, we are reminded that our journey of discovery is only just beginning. Permitting us to notice simply a little piece of its perpetual intricacy. Even with the extension, a significant part of the universe stays dull and purge. In spite of how far we've come in investigating space, its greater part stays concealed. Even with the force of the James Webb Space Telescope, immense segments of the universe stay out of reach. Still, its disclosures proceed to reshape our discernment, offering a brief look into a universe that is more complex and remarkable than ever. The headways brought by the James Webb Space Telescope have not just extended our vision past limits, but have also opened new roads of request. One of the most interesting parts of the telescope's discoveries is the possibility to notice far-off systems as they were in their earliest stages, scarcely a couple 100 million years after the Big Bang. This gives an uncommon look into the early phases of grandiose advancement, permitting researchers to concentrate on the circumstances under which the first stars and cosmic systems formed. Previously, such far-off objects were either undetectable to our telescopes or had to be seen through indirect means. The JWST's utilization of infrared light has changed this. empowering us to look into locales of the universe that were once covered in secrecy. By catching light transmitted from these early worlds, the telescope provides vital pieces of information about the early-stage states of the universe. This enables us to test the processes that led to the formation of cosmic systems, star groups, and black holes in the universe's earliest stages. The JWST's capacity to notice the development of systems at such significant distances challenges many of the traditional models that have long represented how we interpret cosmic system development. For example, past hypotheses propose that the earliest systems would have been more modest, sporadic in shape, and less developed than those seen today. However, the telescope's discoveries show that some of the earliest worlds were already gigantic and somewhat modern, showing complex designs and the kinds of features typically connected with much later, more advanced systems. This raises critical questions about the timeline of large-scale development and whether some cycles happen much quicker than previously thought. Another area where the JWST is making huge contributions is the investigation of exoplanets. The telescope's high-level instruments allow it to notice planets circling far-off stars with exceptional accuracy. These observations provide an abundance of information about the structure and climates of exoplanets, including those that may be livable. By concentrating on the chemical makeup of exoplanetary environments, researchers can search for signs of life, such as the presence of water, methane, or oxygen. The possibility of finding extraterrestrial life has long been an enticing question in the field of astrobiology, and the JWST brings us closer than ever to finding answers. The discovery of potentially livable exoplanets could have significant implications for how we interpret life's presence in the universe. If we find that life-supporting conditions are common throughout the universe, it would suggest that the rise of life on Earth may not be as rare or unique as once thought. On the other hand, if the JWST finds that livable conditions are extremely rare, it could prompt a deeper investigation into the factors that make Earth unique, potentially offering insights into our own origins and the fragility of life. Another area of exploration for the JWST is the study of very large black holes. These mysterious objects, which reside at the centers of most large systems, have long been a subject of interest. The telescope is capable of observing the behavior of material swirling around these black holes, providing a better understanding of their formation and the role they play in the development of galaxies. It is believed that supermassive black holes grow over time by accumulating matter, such as gas and dust, from their surrounding regions. However, the exact mechanisms behind this growth are still not fully understood, and the JWST is uniquely positioned to reveal new insights into this process. In addition to its remarkable discoveries in the field of astronomy, the James Webb Space Telescope has the potential to change how we understand fundamental physics. Its capacity to study the early universe and the formation of celestial objects might help us gain insights into the nature of dark matter and dark energy, two of the most mysterious and elusive aspects of the universe. By observing how galaxies and other structures form and evolve, researchers may be able to detect subtle effects caused by dark matter, which is believed to make up most of the mass in the universe, but does not interact with light in the way regular matter does. The JWST is also capable of probing the nature of dark energy, the mysterious force responsible for the accelerated expansion of the universe. Although we know that dark energy exists, its precise properties remain a mystery. The telescope's ability to track the expansion of the universe over time could provide crucial data to help researchers better understand how dark energy works and how it influences the large-scale structure of the universe. As the James Webb Space Telescope continues its work, it will undoubtedly lead to many more breakthroughs and discoveries that will reshape how we understand the universe. It has already demonstrated its ability to be an invaluable tool for unraveling the mysteries of the universe, from the formation of the first galaxies to the study of exoplanets and the search for extraterrestrial life. As it delves deeper into the vast cosmos, the JWST may provide answers to some of the most profound questions humanity has ever asked, helping us understand not just the universe's past, but also its future. The journey for knowledge about the universe is far from over, and the James Webb Space Telescope is helping us explore this unfamiliar domain with phenomenal accuracy and clarity.